Okay, so yeah, so today we'll just continue talking about this topic of vector spaces. Uh, so the basic idea of a vector space is that essentially like there are certain types of equations or conditions that when you have two elements that satisfy those equations, and let's call them equations. When you have two elements that satisfy those equations, their sum continues to satisfy those equations, and a multiple of them continues to satisfy those equations. So, like the way we would think about a vector space is like the following. Um, let me put this down here. So V is going to be usually the letter for a vector space, or in fact, like there are U, V, and W, the three most common letters for vector spaces. So let me start there. So U, V, W, those are like the common symbols of a vector space. So the difference, like with the notation for like, I mean, like the only thing is that you write it as with uppercase like V instead of like lowercase. If it's lowercase, you actually mean like a single vector. When it's uppercase, you mean like the totality of vectors. So any of these is like usually when we're talking about just like a vector, will a single vector space will just use the letter V, but when there are multiple vector spaces at the same time, then you can use UVW or something like that. Or also V1, V2, V3. I could also put that here as well. So another one would be or V1, V2, V3, etc. So it depends on what you prefer. But the idea of a vector space, like in general, is that it is defined by some conditions. Okay, so it's like it's what usually you call like a set, a set. But if you haven't seen what sets are, it's just like a collection of objects. Defined by some conditions. Okay. Or equations. And it basically what makes this deserve the name of a vector space is that it has the following two properties. So whenever like you have to check that something is a vector space, you need to check the next two properties. So these are like the two properties for a vector space. So the first one is that if you have two elements inside a vector space, so um, if V1 and V2 belong to the vector space, then their sum also belongs to the vector space. Oops. Okay, and then the second, so basically what this is saying is that the sums of vectors continue to satisfy the main equations that define the vector space. And then the second condition is that if you have a vector that belongs in the vector space, and then you multiply it by a number, then the scale vector continues to belong to the vector space. So if you have a vector v inside the vector space, then the rescale vector c times v belongs to the vector space as well. Oops. Here c is any real number. Okay, so in general, to check that something is a vector space, you have to check these two things. And that's more or less what we were going to do today, just do a couple of examples when we'll see whether these two conditions hold or not. That making sense? Yeah, so I'm about to do some examples to show you how this looks like. But again, the key idea to keep in mind is that vector spaces are things where the sum continues to be inside of it and a rescaling of the vector continues to be inside of it. So those are the two main conditions for the vector space. So let me give you some examples. So let's say I had defined something like this. And that way I can also introduce you to some notation of how they are typically written, the vector spaces. So this is typically how you'll see like a vector space written out. So okay, so what does this notation mean? Just to writing word what this means. So that means that you're looking at all the vectors with 3 entries, right? So this means all the vectors with 3 entries, right? That satisfy the two equations that I wrote on the right hand side. So usually there's like a vertical. Usually you write like a vertical line to separate like the name of the vector from like the equations that's supposed to satisfy. So let's call these equations 1 and 2. So it's just saying that we're not looking at random here. Like what this means is that you're not allowed just to put like a random vector inside of it. Instead like the vectors that you should put here like are vectors that satisfy these two equations. So for example, what's a vector that's inside this vector space? So for example, Um, let's see. Right, like for example, if you take 1, 2, 1. So my claim is that 1, 2, 1 is inside of the vector space, is inside of this set, because first, it's easier to check actually the second condition equation first. First, the y coordinate is twice the x coordinate, right? Because x is 1 here, so y is 2, 2 times 1, so that's fine. And then if you do x plus z, that gives you 2, and you subtract 2, you get 0. Okay, so these two equations, I mean, so this vector does satisfy the equation. So you would say that it is inside this vector space, or that it belongs to the vector space. Is that making sense? So this is like a vector that's in here, but which is a vector that's not in here. One that's easy. You could put something. Well, let's put something like just a quick, simple modification on the previous one. So if you just take 1, 2, 0, right? The second equation is satisfied, right? Because y is still 2 times 1. But now the first equation is not satisfied, because if you do x minus y plus c, you get -1 and you don't get 0, right? So this one is not inside B. Since 1 is not satisfied. Is that making sense? So it's not, what I'm trying to say is that here it's not every vector with 3 entries that would be inside this set. Is only the vectors that satisfy equations 1 and 2 simultaneously. So it's not enough just to satisfy one of the two. You need to satisfy both of them, not just one. Is that okay? Are there any questions up to this point? So what we're going to check now is that this is a vector space. So what this means is that if you when being a vector space means in this case is that whenever you take two vectors that satisfy these two equations and you add them together, they continue to satisfy the equations. And if you take a vector that satisfies these equations and you multiply it by a number, it continues to satisfy the equations. So let me just yeah, that's a great question. So in general, I will write that as a remark, because that's especially useful to check that something is not a vector space. But yeah, 0, 0, 0 would have to belong to the vector space. That's actually like that follows from the definition. It's a little bit hidden in here, because if you look at condition 2, right? If you look at condition 2, it says that whenever you have a vector, then a rescaling of that vector should be inside. But C, you could take C equals 0 here, and the moment you take C equals 0, you get that 0 should be inside. So I'll write it as a separate a remark, because it's like a useful way to check that something is not a vector space. But yeah, in general, 0, 0, 0 would need to satisfy the equations. Yes. If it doesn't satisfy it, immediately you would say that it's not a vector space. But yeah, I'll write that. I'll write that after we finish this example, because that's useful too. That's a useful way to check that something is not a vector space. So, but let's start just here. Again, let's start first with just checking that this V is a vector space. So let's check that my claim is that V is a vector space. So again, we have to verify two things. Like the first one is that it has a sum property. So let's check first the sum property. So you take, I hear this is actually kind of like the part of the course that has some sort of like version of proofs. So it's not that the proofs are particularly complicated, but it can get tricky because like just like the writing of it can be confusing, especially at the beginning if someone hasn't been exposed to too many proofs in the past. So it's not so much you'll see, not it's not that the proofs themselves are too complicated, but it just takes some time to get used to how to write them. So here, like, you have to take two vectors inside V. So these are two vectors inside V. What does it mean to be inside V? It means that each of them satisfies both 1 and 2, right? So each satisfies equations 1 and 2. And then I need to check that V1 plus V2 satisfies so I want to check that V1 plus V2 continues to satisfy equations 1 and 2. So I want to check is that making sense? So that's what the sum property says, that whenever you have two vectors that satisfy the original equations, then their sum would satisfy the equations as well. What sometimes is a source of confusion here is on occasion, when someone is trying to prove the sum property, they will give specific entries to the vectors, and you're not supposed to do that. So the vectors you're not checking these for like, for example, you're not checking the sum property for this vector we found. We're kind of trying to check it for any possible vector that could be inside the set. So you're not allowed to just like give specific entries to the vector. So let me write that as a remark, because I think that's essentially where like most confusion occurs. So you're not supposed to give specific entries to V1 and V2. So you don't say that this is like this. Don't say that this is like 1, 2, 1 or something like that. It's not. You're not trying to prove this for a single vector. You're trying to prove it for all possible vectors inside of V, because we're trying to prove this. Okay. So so let's just check again. Let's just check that the sum satisfies equations 1 and 2. So what was equation 1? Equation 1 said that x minus y plus z was 0, right? But now we have to check that for V1 plus V2, right? So for V1 plus V2, that's also like the other thing to realize. Our x in this case is like this one, y is like this one, and z is like this thing. So this is also where the notation, like the notation that you choose, is useful, because if you check the notation, like the notation is like the first entry minus the second entry plus the third entry equals 0. It's just that the first entry happens to be, in this case, x1 plus x2. The second entry is y1 plus y2, and the third entry is c1 plus c2. So this is where, like, also just noticing that is like an important part of the problem. So here, like what I'm trying to say is that we have to do x1 plus x2 minus y1 plus y2 plus z1 plus z2. Is that making sense? So that's what this corresponds to. Is that okay with everyone? Are there any questions about this? Again, that's one of the most important parts in this problem. So it's just that x takes like a specific shape here because it's like the sum. And so we want to check, what we want to check is that this combination equals 0. Okay, so the question is, how do you do it? Well, at some point you will have to use a fact that V1 and V2 individually satisfy the equation. So you'll see how this shows up in a second. But the easiest thing to do that is actually combine the stuff that have kind of like the same index or number. So let's put like the stuff with x1 together and the stuff with ones together and the stuff with twos together, because those are the ones that come from the individual vectors. So this is x1 minus y1 plus c1 . Okay, so there's always a step where you have to regroup things a little bit to make it more clear what's going to happen. But my claim is that now we do know individually what this combination inside each parenthesis is. So what is this equal to? What do you think this would be equal to? So x1 minus y1 plus c1 is actually 0. And this is 0 because v1 belongs to v, right? So this one is 0 because v1 is inside v. Okay, so the condition for v1 to be inside v is that it satisfies a version of this equation, but for its entries, as in its entries were x1, y1, and c1. Is that making sense? So that's why their entries would equate to zero. That combination of the entries equates to 0. And the other one is 0 also by the same reason that each entry is inside because v2 is inside v. Is that making sense? So you would get 0 plus 0, and that's okay, and that's 0, right? So that means that if you combine these, if you check the first equation for the sum, it actually equates to zeros, which is what we needed to make sure it would happen to see that would be satisfied. Is that okay? Are there any questions about this up to this point? Okay, let me do it for equation 2, because again, to check that the sum is inside of this, we have to check that it satisfies 1 and 2. So both need to be satisfied at the same time. So what was equation 2? Equation 2 was that 2x equals y. But again, here we're trying to check that for the sum, right? So what's the sum? What is that for the sum? So we have to check now 2 times x, but x here is now x1 plus x2. Okay, so we have to study 2 times x1 plus x2. That's kind of like 2 times x. Okay, and we have to check whether that gives you y, but y in this case would be y1 plus y2. Okay, so again, like what's tricky sometimes here is just like to identify there are several variables in this problem, so you just have to identify how they're changing. But actually, this one is kind of easy as well. It's just 2x1 plus 2x2. But what can you say about 2x1? What is that equal to? Well, that's y1 because because v1 belongs to b. And this is y2 because v2 is inside b. Okay, so the sum, so this does give you y1 plus y2. So that ends up saying that 2, so this is saying that 2 times the x coordinate is the y coordinates, and that's essentially what you have to check for equation 2. Is that making sense? So that was the first condition for being a vector space, that it satisfies the sum property. So that's the first thing. But there's still one more condition to check, right? So we still have to do the second condition. Is that okay? Let's 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 check the rescaling property, which is the other one that we have to check. So what the rescaling property says is that if a vector belongs to B, its rescalings must belong to B. So if V belongs to V, then its rescalings must belong to V. So must satisfy one and two. So we must satisfy equations one and two. Let me put it like this. Okay, so let's go with equation one as well. Let's start again with equation one. So what it was equation one, it said that x minus y plus c was zero, right? That's, I believe, what equation one says. So now we have to check this equation for c times v, right? So what does that become? These needs to be replaced with the corresponding entries. So x refers to the first entry of the vector, but now the first entry of the vector is cx. So you have to put cx here. The second entry of the vector is cy, so you put minus cy here. And the third entry of the vector is zz. You put that here as well. Okay, so you get something like that. But this is zero because XYZ belongs because V belongs to V. Okay. So that's what the rescaling says. And then you have to do the same for equation two. So what's equation two? Equation two was just that 2x was y. But again, you have to check that for the entries of CV. But what are the entries of CV? Is CX, CY, CG. So what does this look for this particular entries? 2x is just really 2cx. Okay. But 2cx is c2x. But what is 2x? 2x equals y because v is inside of v. So that means that 2cx, that means that 2cx, the twice this first entry gives you the second entry, which was like the condition for satisfying equation two. So that those are the two properties for the vector space. So that's like what we needed to check. Is that making sense? So yeah, in general, like this proves that of checking that something is a vector space. They kind of always look the same as when we just did. They're a bit tedious, but they kind of always have the same structure. So let me make a remark, which is very useful to check that something is not a vector space. So this is a useful remark. So a vector space must always contain a zero vector. Therefore, if the zero vector does not belong to the vector space or to the set V, then it cannot be to a vector space. Therefore, if zero does not belong to V, V cannot be a vector space. So this is very useful in practice to determine that something is not a vector space. Here's an example. Imagine I had given you V to be like the vectors x comma y, where x squared plus y squared equals 1. Okay. So what is that equation of? What anyone recognizes what that is? That's the equation of what? That's the equation of the unit circle, right? On the xy plane. So my claim is that this is not a vector space because the vector 0, 0, right, which is the zero vector, is not inside the unit circle, right? So this is not a vector space since 0, 0 is not in the unit circle. Right, because like 0 squared plus 0 squared is not, it gives you 0, it doesn't give you 1. So making sense? So that's like an example of something that's not a vector space. Here's another example. So now I give you this set And I'm asking you whether this is a vector space or not. So what do you think in this case? First, like we should try to identify it. What does V correspond to? What is V in this picture? It's the first quadrant, right? So V, this is the first quadrant. So what do you think? Would that be a vector space? Yes or no? Let me bring you some coffee while you think about this. So is it or is it not a vector space? Let's see. It actually is not. So it is not. It fails a rescaling property, in fact. So for example, let's take a vector that we know is inside of here. Like you could take the vector, like this could be the vector 2, 1. Okay. 2, 1 is inside of these vectors of this set, right? Because like the condition for being inside the set is that every entry is non-negative, right? So if you take 2, 1, uh, so I have that, and if this were a vector space, then any rescaling would have to be inside the vector space as well. But what happens if you multiply this vector by -2, for example? That is not, it's no longer inside of B, right? So it fails the rescaling property. Is that okay? Is that making sense? Okay, let's continue talking about these vector spaces. So the idea is that there are other things that you can, you know, the interesting about vector space thing about vector spaces is that actually this notion or this definition can be applied to think to collections of matrices or functions. So let me explain what I mean by that. So this idea, so here, what makes the vector spaces useful is that it can be applied to things which you would not ordinarily think as vectors. So the definition, so here's like a remark. The definition of a vector space can be applied to sets consisting of, vectors or functions. It's exactly the same definition. So I'll give you some examples of each so that you see what I mean. Let's start with matrices because, sorry, sets consisting of matrices or functions. Let's start with matrices because it's a little bit easier to process. So I don't know if you remember, uh, that we had spoken about these upper triangular matrices at some point. Let me do it in the 2 by 2 case just to make it more concrete. So this is where it's better sometimes to have a slightly different notation for the entries of a matrix. Usually I have been calling the entries of a matrix like ABC. If you have been reading the book or like anywhere else, like there are other ways to represent the entries of a matrix. You could put like A11, A12, A21, and A22 because like this, like the first like entry refers to the row and the second to the column. So this is first row, first column, first row, second column, second row, first column, and second row, second column. So that's like a convenient way to write the entries of a matrix because it no longer requires you to be using different letters, and it's kind of more like it's more gives more sense of information because it actually refers to the row and column to which the matrix belongs. So I don't know if anyone remembers what it meant to be upper triangular. Is that something someone remembers? I mentioned it briefly when we were talking about the properties of the determinant. Uh, right, upper triangular is something that looked like upper triangular was something where like all the non-zero entries would be above the diagonal or on the diagonal. So upper triangular just means in the 2 by 2 case that the that this third entry is zero. Is that making sense? So being upper triangular just means so being upper triangular is the same as saying that B equals like the 2 by 2 matrices, which are like A11, A12. You can make this zero if you want, and A22. So you're just forcing the second coefficient, the third entry to be zero. Okay. So for to belong in this set, right, you have to be a matrix whose third entry is zero. So for example, A, which is 1, 1, 0, 0, is inside of B, right? But A being like 1, 1, 0, 0 is not in B, right? In fact, like, well, we don't need to give names to these matrices. So this is inside of B because the third entry is zero, but this one is not inside of B because the third entry is not zero. Okay, and so again, like instead of looking at all possible 2 by 2 matrices, you're only looking at those where like the third entry is zero, and so you could ask, does this still have the property that the sum of two upper triangular matrices is upper triangular, and multiplying an upper triangular by a number is upper triangular, right? So my claim is going to be that D is a vector space in that sense. So the claim is that V is a vector space. So what does that mean? It means that it has to have like the sum property, which in this case is saying that the sum of upper triangulars is upper triangular, right? Well, it's actually very easy to check in this case, right? Because what if you happens here if if you have two elements inside of again, remember that sum property means like if you have two elements inside the matrix, sorry, inside the set, then the sum has to be inside the set as well. So here, let's take A to be A11, A12, 0, A22, and V11, V12, 0, V22. So these are two upper triangular matrices. So they're elements of V. What if you add them together? What is the addition equal to? Is A11 plus V11, A12 plus V12, 0, and then V2, A22 plus V22. Is that making sense? So this continues to be upper triangular, right? Is that okay? Are there any questions about this up to this point? So I'm saying like if you took two upper triangular matrices and you add them together, you get a new upper triangular matrix, right? And then the other, so the sum property is satisfied, and then the other property would be the rescaling property. So like the rescaling property says if you take in this case would say if you take an upper triangular, if you multiply it by a number, that product is still an upper triangular. So what we have to check here is like the upper triangular times a number is an upper triangular. So let's check that again. If it's upper triangular, it's A11, A12, 0, A22, and what is C times A? That's just CA11, CA12, 0, and CA22. So if you multiply the matrix, oops, if you multiply the matrix by a scalar or by a number, you continue to have something that's um upper triangular. So this is continues to be upper triangular. Is that okay? So like the way this is phrased is that you would say the space or the set of 2 by 2 upper triangular matrices is a vector space. That's actually what you would see written out. So the set of 2 by 2 upper triangular matrices uh, is a vector space. So vector, the reason why I'm doing this example is to show that vector space is the definition of a vector space is something that gets applied not just to what you would ordinarily think of as vectors, but also can be used to include things like matrices or functions, which I'll do in a second. So, but again, I just want to check that this is making sense in in the in, in this particular case. Is that okay? So let's do another example. Let me let's define this one. So V is not going to be 2 by 2 matrices. Again, V is going to consist of 2 by 2 matrices. So there are 2 by 2 matrices where A is skew symmetric. So A is skew symmetric. I don't know if the other way in which this is also called sometimes is anti-symmetric, but let's call it skew symmetric. So that I think I had told you the definition of a transpose earlier on when we talked about the determinant, but like skew symmetric just means that A transpose is minus A. Okay. So here we're instead of looking at all 2 by 2 matrices, we're just looking at those 2 by 2 matrices where the transpose equals minus A. Um, so let's see. What does that mean? What let's just work out what that would mean in practice. So what is A transpose? Do you remember A transpose? Like the idea of A transpose is that the rows becomes the columns of the matrix, right? So these, which is the first row, becomes the first column of the matrix, and these, which is the second row, becomes the second column of the matrix. Is that making sense? So the transpose was just reversing the rows of columns and rows. Okay. So I want the transpose to be minus A, right? What is minus A? Minus A is just multiplying every coefficient of the matrix A by -1. Right? So what happens when A transpose equals minus A? What do we get? We get that A11, right? Let me put this in color to make it easier to see. But it's A11 equals minus A11, right? So how can a number be minus itself? That just forces that number to be 0, right? So you get A11 equals minus A11. That just forces A11 to be 0, right? Let's like there's another one that's similar to this one, which is the fourth entry. So if you look at this one, it says A22 equals minus A22, and that forces A22 to be 0. Okay, and the other two, they're not quite the same. I mean, they say something useful, but it's not saying that they vanish. It's just saying that one entry is the other, is minus the other one. Oops. So if you notice, these two equations are really saying the same thing, right? Um, oops. These two equations are really saying the same thing because it's just saying that the second entry is minus the third entry, or the third entry is minus that second entry, but that's essentially the same. So these are like the same, like these these are really like the same equation. But so what does that mean? That for a matrix to be skew symmetric, that means that the first and fourth entries have to vanish, right? And for the second entry has to be minus the third entry, or the third entry minus the second entry. So let me just write it this way. So V is really the same as those matrices where the first entry is 0, the fourth entry is 0. Let's just say that the second entry is whatever it wants to be, but then the third entry is forced to be minus A12. Okay, so a matrix of this form is skew symmetric. Is that making sense? So these are all like the skew symmetric 2 by 2 matrices. So what I'm saying, like for example, 0, 1 minus 1, 0, that's inside of B. But if you took something like 0, 1, 1, 0, it's not in B. And also if you took something more silly like 1, 1, 1, 1, that's not in B. So again, for the matrix to be inside of V, the third entry has to be minus the second entry. Okay. Or if you prefer more symmetrically, these two entries have to add up to 0. Okay, but the claim that I'm going to make now is that if you took two matrices that belong here and you add them together, they continue to belong in there, and the same with the rescaling. So what I'm going to show you now is that this V is like a vector space. And again, that means like showing that it satisfies the sum property and that it satisfies the rescaling property. So again, the sum property just means take two elements inside the set, right? Two elements inside the set look like this. The first and fourth entries are 0, and then the third entry is minus the second entry. So that's one way to write them. So you take two elements like that, and when you add them, you get a new element inside of them. So what is A plus B? So it's pretty clear. I mean, it's kind of clear that if you multiply this by -1, you get this. So it's kind of clear that this continues to be skew symmetric. The third entry is minus that one. If you prefer, you can write, to make it more clear, you can write it as 0, A12 plus B12 minus A12 plus B12. 0. So it's clear, like, if you write it this way, it's even more obvious that the third entry is just minus the second entry. So this is like saying that A plus B is skew symmetric again. Okay, that making sense. And then the second property is the rescaling property. So what does it mean to take the rescaling property? It means that if you take an element inside of V, okay, and then you multiply it and you scale it. So you're looking at C times A. Well, it's still clear that, it's still clear that this entry is minus that entry. So still continues to be skew symmetry. Is that okay? So that's why you would call this space. So you would say that the set of skew-symmetric 2x2 matrices is a vector space. Is that okay? Are there any questions up to this point? So again, vector spaces is kind of like a concept where it's vector space just means like sum is inside again and rescalings are inside again. So it's just whatever set has those two properties. So that the sum is contained and the rescalings are contained. So it can be used for something that is not like ordinary vectors in the ordinary sense of the word, but instead like matrices, for example. Let's do one. Okay, let's think about this one. This is a good example to have. So here's another example with matrices. So what do you think about this one? Would this be a vector space or not? So here's my question: is V a vector space or not? So I'm looking at all the matrices, right? I'm looking at all the 2x2 matrices whose determinant equals 0, right? So my question is, would that be a vector space? What do you think? Again, so being a vector space would mean that if you have two matrices whose determinant is zero, the sum would continue to have zero determinant, and the rescaling of that matrix would continue to have zero determinant, right? So the question is, would that be, is that true, yes or no? So how about this? What's the determinant of A? Oh, both the determinant of A and B are zero, right? So each A and B are inside of V. So is that making sense? Because the condition for being inside of V is that your determinant is zero. But what is A plus B? Right, that's A plus B, correct? And what's the determinant of A plus B? That's determinant one, right? So it's no longer in V. So it doesn't, this set doesn't have the sum property, right? So since the sum property fails, this is not a vector space. Is that making sense? So again, like checking if something is a vector space is checking the sum property and the rescaling property. Okay, so let's check. Okay, let me give you some examples with functions. So here are some examples with functions. So let's say that you define a set which consists of those functions. So the functions which are polynomials of degree 2. Degree at most 2. So what does that means? Like what was a polynomial of degree 2 or at most 2? Okay, so let me give you some examples. So for example, f of x, like x squared plus x plus 1 is in V, right? F of x e to the equals e to the x, that's not in V, right? Because e to the x is not a polynomial. What's another thing that's not in V? Sine of x is not in V, right? F of x equals x cubed plus x is not in V, right? Because the degree of the polynomial has to be at most 2, right? And f of x, like let's say 2x plus 1, that's in V because the degree the degree of the polynomial has to be at most 2. So that means that the degree can be 1 or 0. So is that making sense? Like why this is in V, this is in V, and the others are not? So upon here, you're just looking at all the polynomials of degree at most 2. So that can be degree 0, which is a constant, degree 1, which is a line, or degree 2, which is a parabola, right? So V is really it's just like parabolas. It's a parabola, a line, or a line with or a constant, right? In terms of the graph, right? Because a parabola is something of degree 2, if you remember, a line is degree 1, is y equals f of x equals mx plus b, and a constant is like a straight line, so that's also that there's no x there. Okay, so the question now is if you add, like maybe you have thought about that before. If you have two parabolas and you add them together, do you get a parabola? Or if you add like two lines and you add them together, do you get a line? Or what if you add a parabola with a line, do you get a parabola or something else? So what I'm going to show you now is that this space is actually a vector space. So adding two things of degree of two polynomials of degree at most 2 is also a new polynomial of degree at most 2. So okay. So what does that mean? It means like it has to have the sum property. So what does it mean to have the sum property? That you have two polynomials of degree at most 2 and the sum must be a polynomial of degree at most 2. So what is f of x and g of x? You can call f of x like ax squared plus bx plus c. And you can call the other one dx squared plus ex plus f. So these are two polynomials, right? Of degree at most 2, because if the degree is lower than 2, you can just take these constants to be 0. So this covers all the cases. So these are two polynomials. And what is the sum? What is f of x plus g of x? That's ax squared plus bx plus c plus dx squared plus ex plus f. And that's what a plus the x squared plus b plus ex plus c plus f. And that's also another polynomial of degree 2. Or degree at most 2. So this is a polynomial of degree at most 2. Is that making sense? But if you had taken, and if you take also the rescaling property, what is the rescaling property? Well, now you take a polynomial of degree 2. I have to use a different letter here. Otherwise, it will be a little bit confusing. Let's call this like polynomial with, yeah, sorry. Let's call it like, let's call it G. So just keep using G like D, E, F. What is C times G of X? That would be C D X squared plus C E X plus C F. So that's, I mean, that's just like That's just a new polynomial of degree 2. Of degree and those two. So you would call, you would say that this V is a vector space. Okay, so even in this case of functions, as long as it has the property that the sum continues to be inside and the rescalings continue to be inside, you would say that you're dealing with a vector space. Okay. Here's an example that that is not a vector space in the same line. So imagine that I had said, here's another example. Imagine I had defined of the set of polynomials whose degree is exactly 2. So polynomials of degree exactly 2. So what's for example an element in in V is like x squared plus x plus 1, and what's an element in V? Well, also minus x squared plus x plus 1, right? But now if you add them, right? If you add them, you get 2x plus 2, and the degree was lowered, right? And so now since it's no longer at most 2, but it has to be exactly 2, this no longer belongs to V, right? So it has lower degree, so no longer in V. So the sum property fails in this case. In this case. Is that making sense? Is that okay? Is that making sense? So this is not a vector space. So this V is not a vector space. Is that okay? Are there any questions about this? Okay. Let me finish with a slightly more advanced slightly more advanced example, but that's just kind of nice to mention because that's sort of like the way in which this gets used. I don't know if anyone is taking Math 244 or has taken it, so or will plan on taking it. So here's a slightly more advanced example. So it's more advanced because it requires a little bit of calculus. So that's what makes it advanced. So let's see. Mm. Okay. So I don't know if anyone has seen Hooke's law. So the idea in Hooke's law is that you have like a mass connected to a spring. Usually there's like a constant for the spring, which is called K. And so Hooke's law just says that uh, the force on this mass connected to the spring is minus K times X, where X is like maybe the position uh, that you have elongated the spring. So that if you imagine that the spring was in its natural length at x equals 0, and then you have stretched it by an amount x. So the force is just minus k times x. Okay. But I don't know if you remember Newton's second law that the force equals mass times acceleration, right? So sometimes a way you can write Hooke's law is that ma plus kx equals 0. Okay. But I'm not sure if anyone remembers this, but what's the how can you find the acceleration in terms of the position of of the mass? Like there was a way using calculus to find the acceleration from the position. Has anyone seen that before? Well, so the acceleration is a second derivative of the position with respect to time. So again, if you haven't seen that before, don't worry because we won't use calculus in this class. So I'm just putting this like example more like curiosity. So okay, and just to make our lives easier, let's just take m and k to be 1. That doesn't really matter too much. So, but let's take Hooke's law. It's just like it's nicer to so here with for k m equals k equals 1. Uh, so just to focus on the equation itself, the constants, like obviously could take different values from 1, but that's not too important. Does this is sort of like the type of equation you would analyze if you ever take this differential equations class, like Math 244? So this is like Math 244. So it's just saying the position of the mass is a function that has a property that when you add the second derivative to it, you get 0. Okay. So I don't know, again, if anyone has taken calculus here, but I don't know if there's like if you have thought about that before. Like, so let's define a set, which is like the functions of time or functions of t that satisfy the Hooke law. So where like the second derivative of x plus the function itself, it gives you 0. So what's like a function that's in here? Um, so here's like an example. What if you take x of t to be cosine of t? Anyone remembers the derivative of cosine? Again, if you have seen this, if not, don't worry. But anyone knows what the derivative of cosine with respect to t equals? So the derivative of cosine is minus sine, and then when you take the derivative of that again, the derivative of sine is cosine, so you get minus cosine of t. So you see, if you do this in this case, the second derivative plus x is cosine of t minus cosine of t plus cosine of t, and that's 0. So in fact, so what that means is that the function cosine of t is actually inside this set. So the function cosine satisfies the Hooke law. And like again, if you have seen this problem before, it makes sense because when you connect the mass to a spring, it will start oscillating. So there's some periodic motion, and that's why it makes sense for cosine to appear, because cosine is like a periodic function of time. So x of t cosine of t equals is inside of v. Okay, but then like what it's kind of interesting to observe, and that's a lot of what goes into that class of differential equations, is that the set V is like a vector space. So the claim is kind of the set V is a vector space. So that means, what does that mean? It means that it has a sum property. So if you add up two solutions to Hooke's law, you get a new solution to Hooke's law. So what is like, so imagine that you have x1 inside of V and x2 inside of V. Well, what is x1 plus x2? So the question is that inside of V or not? And again, what that means is that you have to check if it satisfies Hooke's law. So what is the second derivative with respect to time of x1 plus x2 plus x1 plus x2? Well, the thing about the derivative is that it's linear. Or if you remember, if you have seen this before, the derivative of a sum is the sum of the derivatives. That's like the same linear. This is sometimes called the linearity property, and that's actually related to the same use of the word linear in this linear algebra course. So it's actually kind of like the same idea. So this is just like a second derivative of x1 with respect to t squared plus the second derivative of x2 with respect to t squared plus x1 plus x2. But then you can kind of combine them. These two go together. So you can say that this is the second derivative of x1 with respect to t squared plus x1. And then you can combine these two together, these other two ones here. And this is zero because it satisfies Hooke's law, since x2 satisfies Hooke. And this is also zero since x2 satisfies, since x1 satisfies Hooke's law. So you get 0 plus 0, and that's 0. So what this is saying is that if you take two solutions that satisfies Hooke's law and you add them together, you get a solution to Hooke's law. Okay, that's kind of cool. And then the last property is the rescaling property. So let's think about that one. Is that if you take so if x of t satisfies Hooke's law, I want to check that c times x of t satisfies Hooke's law as well. But what is that? Well, you have to check the second derivative of c times x plus c times x equals 0. But this is where you have to use the property of the derivative that when you have a constant times a function, you can take out the constant outside the derivative. So this is, again, if you have seen this before, if you haven't taken calculus, this wouldn't make a lot of sense, so that's fine. But the derivative has this property that you can pull out a constant. So this gives you this. And that's 0. Yeah, so you end up with 0. So So what that means is that the solutions to Hooke's law form a vector space. So the solutions to Hooke's law and again, that's kind of useful if I'm not spending too much time on this example because I'm not planning on doing any examples in this class that uses calculus, since calculus is not a requisite or anything. But it's kind of like just useful to mention it because if it's telling you that, like again, if you take this class of differential equations, there are certain differential equations. This is called like a differential equation, by the way, this sort of equation, like Hooke's law. So it's saying that there are certain differential equations which form vector spaces. And that's useful later on in that class because what we will see tomorrow is that once you have a vector space, you can try to find what's called the basis for it. So tomorrow what we will talk about is how to find basis for vector spaces, which in a sense is like kind of like the minimum amount of vectors or elements in the vector space that you need to describe anyone else as a linear combination of them. So we'll talk about that tomorrow. So yeah, tomorrow we'll spend all of class just finding basis for vector spaces, which is like probably the most important concept of a vector space, because once you have that, then you can define the dimension of a vector space, which is the number of basis vectors. So, but yeah, so tomorrow we'll do that, but I just wanted to spend today like giving you some idea of how this is defined in general. So yeah, I don't know if there are any questions, but if not, we can keep talking about this tomorrow.